Hello everyone. We are Group 67 and today we'll present our paper titled Real-Time Facial Expression Recognition using Deep Learning for Enhanced Human-Machine Interactions. Uh, this work was published at the IEEE flagship International BIT conference in December 2024. They are the main authors of this paper and what are they done in this paper? Let's see, the facial expressions are a key part of how we communicate emotions. And this paper mainly focuses on building a real-time system to detect, classify emotions using deep learning, specifically CNNs. The goal is to enhance how humans and machines interact in areas like mental health, education, and security. And what is this paper mainly about? The paper this paper mainly proposes an emotion recognition system for use in many areas. For example, monitoring health, mental health, improving learning through intelligent tutoring systems, and providing better customer experiences.
Thank you, Afrit. I am Misanka. First, I will talk about objective of this study. According to the Builder Deep Learning model, that could accurately detect 7 basic emotions. They are angry, disgust, fear, happy, sad, like that. Secondly, their goal was to enable real-time emotion recognition using webcam input, which means the system could be able to instantly classify emotions from live video. And also, to make the model more robust, they apply data augmentation techniques such as flipping, rotating, or zooming training images. Finally, they wanted to ensure that the system could be used by non-technical users. So they created a simple graphical user interface for easy and real-world testing. Now let's move on to the dataset they use. The model was trained using a FER 2030 dataset, which is a publicly available dataset from Kaggle. It contains a total of more than 35,000 graphical facial images. Every image is labeled with one of the 7 basic images. Before training, they process the data by resizing the images and also apply one hot encoding to the emotion labels and splitting data and into training and testing set. This help prepare the dataset for use the deep learning model. Then move on to the system architecture. This diagram shows overall workflow. It begins with data collection using FER 2030. Then the images go through pre-processing and feature extraction. The features are passed through a deep learning model and the model is trained, evaluated and then tested in real time using web input. This is a real-time work process. Let me explain step by step. The system first captures a live video frame using a webcam. Then it detects the face in the frame using HAR cascade. The face region is cropped, resized and pre-processed. That process image is passed into the CNN model. Finally, the system displays the predicted emotion along with confidence source in real time. This complete workflow allows the system to function live and continuously. Next, Dileshan continue the next part. Thank you.
Let's talk about the CNN architecture. First one is input layer. It takes a grayscale facial image, basically a black and white picture of a face. Then we have block 1, low level feature extraction. This part teaches the computer to see basic things like edges and simple textures on a face. They used filters to find these, and there is a robot layer as well. Next, block 2, mid-level feature detection. Here, computer is putting those basic pieces together, recognizing slightly bigger shapes like the curve and the corner of the mouth. Block 3, high-level feature detection. This is where the computer learns to recognize all facial features like the entire eye or mouth. It is understanding more complex patterns. Then block 4, deep feature encoding. This block focuses on very fine detail. Finally, the fully connected layers. All the learned facial information is gathered here. The last part has 7 categories, each representing an emotion. The program detects the correct emotions for the face in real time. The team used a specific learning strategy called ADAM to help to learn efficient, and the loss function is categorical cross-entropy, and the total epochs are 48 and the batches are 32. Horizontal flips and small rotations were used for the data augmentation part. Let's talk about the GUI. Initially, the user simply click a start button, which activates the computer's web camera. Once activated, the system will display the detected face and its identified emotion live on the screen. The interface was specifically designed to non-technical users, ensuring broad accessibility.
Thank you, Dilakshan. Let's briefly see how the system performs in real time. The authors implemented real-time emotion detection using OpenCV integrated with a custom graphical user interface. As shown in the example image here, the system uses webcam input to detect faces and classify the dominant emotion for each face in the frame. One major strength of the system is its ability to analyze both single and multiple faces simultaneously. This makes it practical for real-world group settings, like classrooms or meetings, where multiple people may need to be evaluated at once. Moving on to performance, the authors compared two different CNN models. Model A, which did not include data augmentation, achieved a validation accuracy of 58.6% using deeper convolutional and dense layers. Model B applied data augmentation techniques like horizontal flips and slight image rotations. This model reached a higher accuracy of 75.97%, making it state of the art on the FER 2013 dataset. These results clearly demonstrate the impact of augmentation in improving the model's ability to generalize and handle variability in facial inputs. As for future directions, the paper outlines several interesting improvements. The first goal is to introduce additional emotion classes such as confusion or boredom, which are especially valuable in education and mental health contexts. Secondly, the authors aim to make the system more robust against real-world limitations such as poor lighting, partially hidden faces, or background clutters. There's also interest in expanding to multimodal emotion detection, combining facial expression with voice tone analysis for more accurate and natural emotion recognition. Lastly, The paper acknowledged the need to account for cultural differences in how emotions are expressed, which could improve the model's fairness and applicability. To wrap up, this paper presents a deep learning-based system for real-time facial emotion recognition. With an impressive 75.97% accuracy, the system shows practically viability and outperforms previous benchmarks on the FER 2013 dataset. Its ability to run in real time using webcam input and to work with multiple faces makes it a powerful tool for applications in human-computer interaction, education, healthcare, and surveillance. The research also opens up several pathways for future innovation in refinement. That concludes our group's presentation on the selected conference paper. We hope this review helped highlight both the strengths and future potential of this work. Thank you for your attention.